So continuing on, we're looking at two more examples, and we're going to be using here the limit comparison test because the regular comparison test just would fail for both of them. So we're going to start by looking at an, and an in the first one is 2n squared plus n divided by n cubed minus 3n squared plus 4, and we have bn. Bn is going to be what? So here's the decision we have to make. What's going to be our choice for Bn? So we look at this and we're going to try to determine which are the dominant terms. Which are the terms here that matter as n gets increasingly large? Which are the terms that directly affect whether it converges or diverges? So in the numerator, okay, we have this n term. We're going to ignore that as a lesser degree. And in the denominator, we know that here this n to the power of 3, that's the dominant term. So I'm going to ignore this 4, and I'm going to ignore also this negative 3n squared. So my choice for Bn is going to be n squared divided by n to the power of 3. And we already saw in the last video I could include here 2 if I wanted to, or I could leave it out. But for now, let's just leave it out. Okay, we end up with n squared over n to the power of 3. That's going to directly be 1 over n. That's p series. It's actually the harmonic series because p is equal to 1. So if p is equal to 1, it is going to be divergent p series. And so our belief right now is that an, the sum of an, would also be divergent. You will notice trying to get the inequality in the right direction, trying to show here that an is larger than or equal to bn is not going to work out nicely, or it'll be a little bit more complicated than we would like. So let's just go and directly look at the limit comparison test. So we're going to check what is the limit as n approaches infinity, an divided by bn. And so an, we can write that in. We have 2n squared plus n divided by n to the 3 minus 3n squared plus 4. And here we're going to multiply by the reciprocal of bn, which is just n over 1, or just n. And now you could, again, look at this, and using the shortcut that we've talked about, you could know that this limit is going to be just 2 divided by 1, okay, because here I have degree 3 in the numerator, degree 3 in the denominator, and so the ratio of the coefficients will be 2 divided by 1. However, let's just go through quickly the steps as to how we would prove this. We have that the highest power of n in the denominator is n to the 3, and in the numerator we have the same thing. So here let's factor n to the 3 from both of them. We end up with 1 minus 3 over n plus 4 over n squared. In the numerator, if I do the same thing, I end up with 2 plus 1 over n, and now we clean this up, and as n approaches infinity, we get any of these terms is going to go to 0. So as we saw, our limit is just going to be equal to 2 divided by 1. The limit is 2. And here, you think for a minute, which test are we doing? What do we care about for this result? This is the limit comparison test, and so the only thing that we're interested in is whether this limit exists and if it's equal to 0 or not. And for this one, the limit does exist. It's also not equal to 0, so that means that an and bn both go to 0 at the same speed, and so in this case they are both going to be divergent series. So we have that therefore an is also divergent by the limit comparison test. Okay, and so that's it for that one. Okay, no matter how complicated the polynomials get here, we're still just looking at the dominant terms. So let's take a look at this fourth example, and here again we're looking to use the limit comparison test where an is 2 plus 3 to the n divided by 4 to the n plus 5n, and we want to know what is going to be our choice of bn. What are going to be the dominant terms here? So in the numerator, here this should come as no surprise. We have an exponential function, and we have a constant function. So this constant term, that's not going to matter as n goes to infinity. That exponential is going to be the term that determines the rate of growth. Now in the denominator, what do we have? We have an exponential here, and we have just a linear term, 5n. And so here we need to know that this exponential term is going to be the one that goes to infinity faster than 5 times n. And so this 5n term, that is the one that does not matter. So in this case, we have our dominant term in the numerator is exponential, and our dominant term in the denominator is also an exponential. We have 3 to the n divided by 4 to the n. So now we're going to compare it to this. However, what type of series is Bn? Well, you have to recognize that here we have only those exponential functions, so this means it's a geometric series. We could rewrite it like this to determine what our common ratio is. So we have r is equal to 3 divided by 4, and here again we would normally be interested in absolute value of r. That's going to be less than 1, and so that means that this is a convergent geometric series. And so at this point, we would be assuming that an is also going to be convergent, but we have to check using the limit comparison test what that limit is going to be. So here, what's the limit as n approaches infinity of an over bn? So we have an is 2 plus 3 to the n divided by 4 to the n plus 5n. And I'm going to multiply that by the reciprocal of bn, which was 4 to the n over 3 to the n. Now here, of course, we're going to have infinity divided by infinity, and the technique that we use to evaluate this limit to get rid of that indeterminate form is going to be one that you might not be otherwise familiar with. So here, if you're seeing it for the first time, this is one way of dealing with that infinity divided by infinity when we have these exponentials. So the real problem right off the bat is that if you start using L'Hopital's rule, well, these exponentials are not going to go anywhere, right? We know that the derivative of 3 to the n, for example, that's just going to give us 3 to the n ln of 3, and the same for 4 to the n and so on. So here, we could get rid of some of the terms by doing L'Hopital's rule. We could get rid of these ones. They'll go away, but those exponentials are going to stick around and constantly keep giving us indeterminate forms. So instead, what we can do is factor. From the denominator, I'm going to factor out 4 to the power of n, and that leaves me with 1 plus 5n over 4 to the power of n. And in the numerator, I'm going to factor out 3 to the n, and that leaves me with 2 over 3 to the n plus 1. And I still have here on the side multiplied by 4 to the n divided by 3 to the n. And so now let's take a look at what we actually have. And right away you'll notice that a lot of this is just going to simplify nicely. I can cancel out this 3 to the n with this 3 to the n. I could also cancel out this 4 to the n with this 4 to the n. And then I want to know what happens to these two terms. Well, this one in the numerator, it clearly goes to 2 divided by infinity, so it's going to go to 0. And here in the denominator, I have 5n over 4 to the n. That's going to go to infinity over infinity. So we can sort of go off to the side, though, and check what happens with L'Hopital's rule if I do the limit as n goes to infinity of 5n over 4 to the n. I'm going to get limit of just the constant 5 over 4 to the n ln of 4. And so maybe this comes as no surprise. You get 5 over an infinitely large number. You end up with 0, which means in this case that term in the denominator, it also goes to 0. So we don't need to worry about it. And actually, we no longer have an indeterminate form at all. We have a 1 in the numerator. Okay, this 1 is the only thing that doesn't disappear. And we have this 1 here in the denominator that also doesn't disappear. So we have a limit of 1 over 1. Our limit is 1. And again, for the limit comparison test, all we care about is that that term is non-zero and that it exists. And so our conclusion is going to be that AN is also convergent by the limit comparison test. Okay, so again, you want to make sure you get more and more comfortable coming up with these choices. For Bn, you need to start to think about which terms matter and which terms do not as n goes to infinity. Which are the dominant terms? They're the ones that determine your choice of Bn. And otherwise, that's it for both the limit comparison test and the regular comparison test. What we're going to be looking at in the next set of videos is going to be the two final tests that we're going to look at, which are the ratio test and the root test. They are very similar to each other in statement. Okay, and so when you are trying to remember all of the tests, you're going to constantly be remembering those two together in the same way that you're likely to remember the comparison test together with the limit comparison test.